Welcome to this Codurance meeting. I'm Ignacio Saporiti. I'm a software craftsman at Codurance, and I will be your host today. Today's talk is given by Javier Martínez. He's a data engineer at Wefox with expertise in Python and a variety of databases. And today's talk is called Graphing Your APIs, Simple Service with Python based on GraphQL and Neo4J. Codurance was born from community and meetups like this, so it believes in giving back. So if you have any talk you think you're willing to give to the community, feel free to get in contact with us, and we can organize a new meeting like this one. So thank you again, and I will leave you with Javier. Enjoy.
So hi, thank you for the nice introduction, Nacho, and welcome everybody. I will start sharing my screen. The session of today will be focused on talking about graphs in your API. And the goals of these sessions, I want you to make it clear that this is a session for learning, for coding happily, to provide value to you, to the community, and to research together about a given topic. As I was talking with Nacho before, I'm not a super expert, so this is an open conversation. I'm more than happy to talk with you, to accept any question, or even in the future, if you want to ask any question, just remind you that you have the repository, which is under this URL, and you can open pull requests. You have my information and all the information of the session in this README. Well, you can reach me at any moment. Okay. So how are we going to schedule or structure the session? The plan is to review a little bit some concepts, to have a common language, that we don't get misunderstandings. So the next thing, or the next step, will be to review a bit the technologies, but this will be short. What I want to focus your attention is in the practical part. Okay, so we will go through a use case, and we will try to apply the technologies to this use case. And at the end, we will do, or I hope we can do together, some recap or summarize some ideas. Okay. So to start with some definition is what is a graph, and the Wikipedia is relatively easy to grasp the concept. So graph is a structure amounting to a set of objects in which some pairs of the objects are in some sense related. So I'm not an expert, but I provide here my definition. But the key point is to focus our attention on the entities, on the relationships. Okay. Below the desk here, you see, or you can see the depiction of a graph, and this is really intuitive for us as humans. You can see that we have some circles, which are the nodes, and we label them to identify them. There are some lines connecting these nodes, which are the relationships. So basically, a graph is some sort of entities that are meaningful in our domain, that has some relationship that is also meaningful in our domain. Okay, let's keep it like that. It's not the perfect definition, but hopefully it's enough. So the second thing that I want to do is to review a little bit the technologies. The whole session will be in Python, and the reason is that mainly I develop in Python, and we are going to use 4 packages. The first one is Fast API, because I think it's an excellent framework for developing APIs, and has nice features for integrating GraphQL. The second will be Graphene, because basically Fast API is using Graphene underneath. and Graphene is the package to deal with GraphQL in the Python ecosystem. Then we will use Neo model, which is the OGM, which is similar to a ORM, an object relational mapper, but in this case, it's an object graph mapper. Okay. We will use the Neo4J driver, okay, to perform some specific queries. This is from the Python perspective. And then let's focus on the specific technologies that are related with graphs somehow. The first one is GraphQL, which is a language on top of a schema, okay? Is a new paradigm, let's say, compared to the classical REST API, in which once we have the contract, which is the schema, we don't need to access different endpoints to retrieve or perform operations on the data. We just launch queries against this schema, okay? And the idea of the name, I think, of GraphQL comes from the idea of traversing that schema that you have defined and then retrieving or dealing with the data as you want. So because it's a paradigm, it also brings new concepts like mutation, subscription, resolvers that could be, well, new for you or scary, but we don't need to worry too much, and we will review it during the coding session, okay? If any of you is an expert in GraphQL, I'm more than welcome to listen any comment about it. The second main technology that we are going to use is Neo4J, and Neo4J is a graph database, which is kind of an object-oriented database and a relational database. But the key point is that it's really efficient when dealing with data that is structured as a graph, as a network. Why? Because the graph traversal. So the engine is really efficient, jumping from one node to the other and performing operations in that way. So within this database, one can define nodes and relationships. And those nodes and relationships are entities by themselves, and one can play with that to store the data and to store the information. One of the key advantages of Neo4j is that it also provides a really powerful engine of data science and a neat set of tools of statistic and graph statistic, okay? So at the end, it's just another container for data. Depends on the domain we are working on. Could be really useful, or depends on the final result that we want to achieve. Could be really useful or not. So it's kind of like the water, no? Depends on the container. You can do something with water or a different stuff. With data, it's kind of similar. You can do many stuff, but sometimes the container of the data also helps to perform some operations, okay? So this is the theoretical part. Now I want you to switch to the practical mode. And my idea for this session is to drive the whole session with a practical use case, and will be like this. Imagine that we are a telecommunication provider, okay? And we want a system to analyze the network of communication towers that we have, okay? So we need to develop a communication tower analysis system, CTAS, okay? And the system that we want to develop should be able to set new communication towers, change the properties, But also we need to retrieve or to compute how critical a tower is within that network, okay? Because in case one of the tower is really important for the whole network, we should be aware of that and maybe implement more safety methods or security methods, okay? So the idea is depicted here. We have different towers. We are the orange guy, and we want to develop a blue box, which is our system or API that should be aware of the towers and the relationship between towers. And for instance, in this case, the most critical tower will be this, because if it gets affected by a lightning bolt or something like that, we will have the whole network split in two, and that will be really critical for the whole communication. Okay, so this is the toy example that we want to deal with and implement. So, and now it comes the coding time. Again, you have all the code in the repository. I structure it in different branches. So the master branch has only the README, so no code. So we will go through the first step in which we review how to query or perform simple queries with GraphQL. Step 2, we will perform more complex queries. And in step 3, we will analyze or deal with mutations in GraphQL, okay? In step 4, we will mix a repository layer based on Neo4J with the GraphQL. And in step 5, we will use some of the neat features of the engine of Neo4J to retrieve this criticality score, okay, of the network. So the idea is that I will go through the code and explain you what it's doing and why it's doing. If you have any question, please jump in and ask me. So I will switch to the IDE, to Visual Code. So the first thing is to git checkout to step 1. Okay. Git stash. Moment. Git checkout step 1. Please remove. 1 second. Let's delete the garbage. I think we don't need to do this. Okay, we are now in the branch step 1. Okay, so the idea is that we have all the code within this folder, the CTAS source code folder. Okay, and in this branch we have only a main file, and the main file, like is right now, depict or shows you a really basic REST API written with fast API. Okay, so what we are doing is in line 27, we are defining an application with fast API. And in line 30 to 32, we are defining an endpoint. I have between line 6 and 12, I have a super simple database. So it's just a dictionary in memory. So where we store the ID, which will be the number, and the name of the tower, okay, of this telecommunication system. And this will be the classical implementation, of course, much more complex in a REST API. If we run it with the server, with Ubicorn, with this command, we will start the server. We go to the local host. Okay, there's nothing. This is a neat feature or really nice feature of Fast API that it implements Open API, so we can go to docs and we will have this UI for playing with the data. Okay. So our system needs to retrieve some information, query information about the towers. Okay. So what we will do in the classical REST API, we will have a get endpoint and we will pass one parameter, for instance, one, and we will execute it and we will retrieve here the name of the tower, okay, from the database, which in this case is a dictionary, as I said. If we retrieve number 2, we will have tower 2. And if we try to retrieve number 54, we will have null because we don't have such a tower in the dictionary, okay? So the idea that I want you to show with this example is how to the transition between this paradigm to the GraphQL paradigm, okay? And how it's integrated within the Graph and the Fast API, okay? So if we want to do that, we will need to comment this out, okay? And I will uncomment this and this, okay? And let me explain. First, I will explain you this part. The same way as we defined before a get endpoint, now we define a new route, sorry. In this case, at the root level, okay? We need to pass something called GraphQL application. It's coming from the startLead package. And why? So the structure or dependencies in the Fast API environment is like this. Fast API is at the top. So Fast API depends on startLead, okay? And startLead depends on Graphene, okay? For dealing with GraphQL. So that's why we need to import from startLead the GraphQL application. Well, let's see the other elements. When we define a GraphQL application, as I mentioned before, GraphQL is based on a contract, and that contract is the schema, and the schema is the thing that we will be able to query. Okay, so the main parameter of that application is the schema. For generating the schema, we just call the constructor here and pass, in this case, the query parameter. The query parameter will define with what kind of queries we can throw, we can run against that schema. Okay. In GraphQL, there are mainly three object types, which are the queries, the mutations, and the subscriptions. Okay. In this session, we are going to review only the queries and the mutations. Why? Because the queries are the objects or the definition that allow us to retrieve information from the domain. And the mutations are the operations that allows us to change that information in our domain, okay? In this simple example, as we did before, we want just to retrieve information from the database, from this simple database, okay? In the case of GraphQL, the queries, or in Python environment ecosystem, is GraphQL is based on Graphene, or Graphene is the library for using GraphQL in Python, okay? And the query inherit from object type, okay? That is coming from the Graphene package. The relevant part, or the way we need to think and to define queries in this type of objects is like the parameters of the object will be the things that we want to query, okay? So in this case, what we are saying is we want to be able to query the tower name, which is what we have here inside the dictionary, and that will be a string, okay? And for retrieving that information, let's say that graphene is agnostic, has no idea, depends on us, on the developers, on the owners, to define what does it mean for the consumers of this, or how to resolve these situations or these queries. That's why for each parameter that we define or that we want to query, we need to define a method called resolve underscore and the name of the parameter. Okay. In this case, tower name is the name of the parameter. So to perform the query, we need to write a method called resolve underscore tower name. Okay. So if we save this and we go to the local host, what we will find is this interface, okay? And this is this GraphQL is a simple UI to perform queries against our schema, okay? It's something that is already built in Graphene. What allows us is to write here whatever queries, and we will see the result in the right part, okay? It also has here some docs, which based on the types that we have defined, we can navigate through the different, let's say, parts of the schema, okay? But how to do a query once we have this? So the way of querying is open the curly brackets and write the parameter basically that we wrote here, but instead of snake case will be camel case, tower name, okay? And if we run it like this, we will have null. Why? Because we are not selecting what we want to query according to the logic, and we will review that. So if I try to query hello, that is something that is not defined. There is no hello parameter here. So, sorry, what we will have will be an error, and the error will be cannot query hello, basically because it's not there. Okay. So basically, the resolver has the logic to retrieve based on the ID, the name of the tower. The ID is defined as a parameter here. So when you define the type of the parameter that you want to query, you define also the argument that you will pass for perform that operation. To query, you will do something like this: ID 4. And if you query, you will retrieve the tower number 4. Okay. Because we are a bit late, I will go super fast, and I assume that this idea is clear. So let's progress. This is nice, but we want to do something more complex. So we will check out. Let me do something. Okay. Let's jump to, don't save, let me close everything. Okay, in step 2, in this branch, we are going to do more complex queries, okay? And that's why I split a little bit the logic in 3 files. We have the main, which has the logic of the application. We have the models, and we have the query, okay? And the query is defined more or less similar. We have the query, and we have one parameter. In this case, it's not tower's name, but towers, okay? And we have the resolver function here. The difference is that we create a more complex model. So we have now the tower ID, the gigahertz band of the tower, the power, the country, the providers, and the links, okay? Links is the links with other communication towers. The way of defining this relationship in GraphQL is by calling a lambda that refers to the object, to the class itself, okay, when it's a relationship with yourself. If we go to the query, what I have done is to generate some toy data, initial data. So we have communication tower 1, communication tower 2, and communication tower 3, okay? And the number 3 is related to a communication tower 1, okay? And this is the database. In this case, it's a list of towers. It's not a dictionary, okay? But the way of working with that is the same. I will refresh, sorry. I will start the server again, and I will refresh here to go to the local host. Okay, so we have the same interface as before. The difference, and I will reuse this query, is this. Now, well, let me write it. It's really fast. We can define towers because this is the parameter that we want to look for or query. But now we accept different parameters: ID, country, and max power. So what we can do right now is a more complex query in which we say, okay, I want the towers that are located in Spain, for instance. I will open new brackets and I will tell, okay, from the results, I just want the tower ID. Okay. And I comment this out. And if I run this, what we have here is that the data that was returned by the API are just the tower IDs, not the whole information about the tower. But the neat thing or the nice feature of GraphQL is, what if I need more data? Maybe in a traditional REST API, you will need to implement a new endpoint or something similar, change the contract. In this case, what you can do is just, okay, instead of returning just the tower ID, give me also, well, not the country, but the power, okay? And if we query, we will get, in addition, the power. What if we want also the links? Okay, in this case, if we do this, I don't know if you notice, automatically the browser add the properties of a tower. Why? What is this case? Because the links is an array of towers. So you need to query something or specify the information that you want to query about these towers, okay? So when we query this, we get the tower ID at the first level, and within links, we query or we obtain also the tower ID, the gigahertz band, the power, and the country, okay? So this is a way of performing more complex queries. You just have to increase a little bit the complexity of the model, and implementing this as parameter in the query class and the resolver, you will have the proper result, okay? So let's progress. So what if we want to do now, not just query, but we want to also modify the data that we have stored in our database. So let's jump git checkout to the step 3. And in the step 3, what I have done is to, and I will present you, is to add a new file, which is mutations. I mentioned before that mutation is the way that GraphQL has to add new data or modify the data that you have defined in your schema, okay? So you can check that the query is similar to what we have before. We have the same database as a list in memory. The models are exactly the same, and the main is also exactly the same. Nothing changed. But not, well, sorry, something changed. The mutation should be passed as a parameter to the schema, okay? So we are implementing mutation in the mutation.py file and importing the class mutation and we are passing it as a parameter of the schema, okay? This is needed for graphing to understand that you are going to use those mutations. Okay, what we need to do about mutations. I have implemented two mutations, add tower and remove tower, okay? But we will focus just in add tower. The object that we import and we put it as a parameter in the schema is a mutation, okay? And this an object type. And what we are doing here is to define a list of mutations. Each parameter, add tower and remove tower, are fields that we want to mutate, or operations that we want to do on our model, okay? So add tower is a class by itself, and the way of this, similar to before, what we do with add tower is, okay, add tower is an operation on the domain, okay? And the arguments to modify will be here, defined in an inner class called arguments, okay? So in this case, we define, we require an ID. Why? Because we want to add a new tower, and this new tower should have a new ID, okay? And this is required. The parameters of this class are telling, okay, I'm doing this operation, and in return, I will like to have a tower and an OK field. The OK field is just to retrieve whether the operation was okay, and the tower will retrieve or will give back the tower that we just add to the database, okay, with this action. And similar to the resolvers that we have seen before, as a convention, each mutation class should have this method, mutate, that defines how the data will change in the database, okay? So what we are doing here is check whether the ID is already in the database, and check whether we have data to add, or we just want to create a vanilla communication tower, okay? You can review the logic within mutate, but let me turn the server up on, and we will check the result. So if we query the databases by, well, we can just, oh, sorry, by just querying like this, tower tower ID. If we query like this, cannot current server, because this is using, sorry, let me refresh it. Do you mean tower ID or tower? Sorry. Okay. These are, let me also put the country here to have more information. These are the towers that we have already in the database, okay? What we want to do is to add a new tower. So for performing a mutation, instead of querying like this, one should define a mutation and then open the curly braces, okay? I will reuse this example here, okay? So you can check that a mutation should have this keyword before the curly braces, and we need to call the query method that we implemented as a mutation at tower. In this case, we have 1, 2, 3, and we want to add the 32, and we want to add it with this with this data. And in this case, what we want to return back is just the OK. If we do this, because this is providers and this is Movistar. So if we do this, the system of the API responds, OK, that works. Okay. And if we check again how many towers do we have, you see that we increase the number of towers in one. Okay, so our mutation is working. I would like to have more time to explain it to you, but I think you grasp the the idea. If not, let me know and I will explain you in depth. So now we have a method or a way to modify data in our system with GraphQL. Okay, so the next logic step is to improve the repository or the database. I mean, working with dictionaries or lists in memory is not really efficient. So let's get a step to the step number 4, to the branch number 4. Okay. In this branch, what I want to show you is how to integrate Neo4J into the equation, okay, into the scene. So first thing that you will notice is that there is a Docker compose. Okay, the Docker compose is set up already to build up an image of Neo4J. So for working with that, if you worked before with Docker compose, you just have to Docker compose app in this folder. And well, I already have the image and I worked before, but it will work pretty neat. So important environment variables here are Neo4j auth, and you have to pass Neo4j, which will be the user, and dash JJ will be the password. And of course, it's really, really safe password, JJ. So for a toy example, it's not so bad. And this is really important too, the Neo4j labs, because this will allow us to add the plugin of Graph Data Science, the GDS, that will allow us in the next step to perform some operation and define this criticality level, okay, that I mentioned before at the beginning. So in this case, and just to show you, if the Docker is telling us, okay, you can go to the 7474, and if we go, you can see this really beautiful interface that the people of Neo4j design. It will ask you always to register with username and password, which is JJ, and you can connect. And you can check what you have. I mean, I will not go in detail on how to use Cypher and the interface. Cypher is the query language for, well, it's not a standard, but almost, of graph databases. So this field here will be the place where you put your queries. Sometimes if you have some other labels, you can just click and you will have the structure of a network, and so on and so forth, okay? But let's review what we have in our domain, okay? So we have the main file, the models, mutations, and query, okay? These are 4 files that we had before in the step 3. But now in the step 4, we add a new one, which is the repository, okay? Repository, what it's doing is defining the functions that will allow us to store data in in Neo4j, okay? But before that, we need to review a bit the models. Before we had only the models related to GraphQL, but now because we are going to use the graph database Neo4j, we want to add a new entity in our domain into the repository. Of course, it's not the same because we are using different libraries, but we have a new type of model right now, which is the structure node. And this structure node is coming from the Neo model library that I mentioned at the beginning that we are going to use to work as a OGM as an interface of our domain, okay, to perform operations on the graph database. If you check the model of the of the GraphQL and the model of the Neo4j is really pretty similar, okay? So the mismatch is relatively low. In the repository, if we check it, instead of having, well, we have as before, the tower 1, 2, 3 that we had the list that we had before, but this is not any more the database or the repository. Is just to set an initial state of the network, okay? So whenever we start the application here in the main, we will call initialize DB that is calling using this function to clear all the existing nodes with this command from the Neo model library, and then using toCompTower method to generate this set of this list of towers, okay? So the toCompTower function, what it's doing is accept a communication tower input and will convert it, and more important, will store it in Neo4j, okay? The other method is toCommunicationTower, that what it's doing is accepting a communication tower and translating to a GraphQL model, okay? Let's go and start the application. So because at the beginning, we are running the initialization of the database, if we go here to the CompTower, okay, you see that we have tower number 1 with all the parameters, gigahertz band, power, country, provider, that we gave in our code, and also the links. If you see the tower 3 that was linked to tower 1, now has or presents this relationship within Neo4j. And this is really special because the relationship is something with entity within the framework of Neo4j, and is what offers some capabilities of it. I recommend you to review how the mutations and queries were modified, because of course we don't need to query the dictionary or the list anymore. What we can do right now is, if I want to query, I just go to the to the Neo model, okay? This CompTower is coming, or is a model written with the Neo model library. And because of that, what we can do is telling, okay, Neo model, you know that I have CompTower's nodes in the database, like you see here. So from these nodes, give me all of them. And the OGM, what we'll do for you is to query the database and return a nice set of results. And then later on, we only have to call the toCommunicationTower to fulfill the mismatch between the database and the GraphQL, okay? If there is an error, we will return an error. If we go to our beloved interface, we have the same basically. So we can query the towers in the same way. Okay. Even before, even better links, and we want tower ID. So we can do it similarly. Realize that now it's a bit different because in Neo4J we are saying, okay, this relationship is undirected. So for Neo4J relationship, I mean, tower 1 is linked to tower 3, and tower 3 is linked to tower 1. Okay, that's why it's a bit different than before, because now tower 3 that before referred to tower 1, that was like before, but now tower 1 also refers to tower 3. Okay, so and what happened if we add a new, or we want to perform a mutation? So let me change this, because one of the changes I did is that in step 3 I implement the providers as an enumeration. So in step 4 I decided to simplify it and pass it as a string. So let's do it like this. If we run this, we got a response, okay, your node was created in the database in your domain. So we can go to the ground truth, which is the database, and check what is there. Oh, and this is what we have. We have a new node here. I don't know if you had time to review. A new node, we gave it the ID 32 with the links to 1 and 2, okay? To tower 1 and tower 2. And what we have created is just a new tower 32 with links to 1 and 2. We can also create another tower 44 with a link to 2, 2 and 3, for instance. Okay, and if we query again, we will have this nice shape pentagon. So we will have this new tower in the network. Okay, so what we have achieved in this step is to integrate a GraphQL with a nice graph-based database, which is Neo4J, so that we can, from an external UI, for instance, query the API to query GraphQL, and this will go to the graph database, retrieve the information, or perform the operations that were needed for generating towers of node. Okay, so the last step is, okay, now let's say we are able to generate a network. We just did it in this, as you can see in this example. So what we need now, according to our use case, is to perform some kind of measurement of the network. In this case, we define the criticality, and the criticality is based on a mathematical concept called betweenness. You can research and look for betweenness in the graph theory, and you will find what it is. Is when you traverse the the graph, the more a node is in the middle of a path between two nodes, the more is the betweenness of that node. So the more critical, in the sense of what happens if that node is not present in the network anymore. Okay, so let's check what we need to perform this kind of measurement. Let's check out to step number 5. And in step number 5, the whole picture more or less stay the same. We have 5 files. Mine the models did not change much, but we add this betweenness object type for GraphQL because we want to query now this new model, new entity. So we need to define it within GraphQL for being able to query. Okay. Betweenness will return the ID of the tower and the score of this parameter. Okay. The mutations did not change much. The queries did not change much. The only thing is that because now we want to query what is the criticality or relevance of a node within the network, we need to add this parameter to the query object. And as I said before, to resolve, to be able to query in the way we want, we need to implement this resolve relevance method. Remember that this is the convention, resolve underscore relevance in graphing, okay? For the repository, I generate a class because before was too simple. And the class contains most of the methods that we have before, but some more, okay? So in this case, we are going to use also the Neo4J driver, okay, which is this library here, Neo4J. And we want to have some exceptions, and that's why I put it here. To define the connection with the database in this driver, we need to do this stuff here. That's why it's in the initial init of the creation constructor of the object, sorry. As you notice, I get rid of the toy database because I changed a little bit the initialize database. Okay, so what we are going to do is to clean and to generate a network, okay, at the beginning of the application. And this is done in this step, okay? At the beginning, at the startup of the application, we clean the database, we initialize the database, and then we generate the network with a number of nodes, 8, and a level of connectivity equal to 2, okay? This is something I made up, so it's not established in the framework, or it's just generating a network with the logic that you can find within this method, okay? The com tower and the communication tower method are the same, exactly the same, okay? Then we have start graph and get betweenness score, okay? And these two methods are using the Neo4j driver to perform direct queries to Neo4j. And the reason for that is because you can see here, we want to use this plugin that I mentioned before, the GDS, to create, to analyze, or to get some science from the networks. So the first step for that is to generate a graph, because usually you don't, or you may not want to work with the whole network that you have in the database. So you can take or define a graph with a subset of that, okay? If you don't know, I mean, this is a Cypher language that this could be copy and paste directly here, and you will get a valid result, okay? By starting the graph is just, we are saying, okay, we want a graph called like this, whose members will be com tower, and that will have a relationship called link, okay, and that is undirected, and each link has no specific weight, all of them weight 1, okay? Because, well, in this case, the connection between towers is similar. And the and the function get betweenness score is doing also kind of, well, it's using also the GDS, but is running against the database with the driver, with the Neo4J driver, and is computing this betweenness, okay, parameter that I mentioned before. And this is the beauty of the solution in my mind, because it's like, okay, you have a perfect tool for dealing with graphs, and you can run and perform operations directly in the database and retrieve that. And I think this is important and bring really benefits, because I mean, I'm just using the betweenness, but what if you want to do more complex stuff? Well, Graph Neo4j is optimized for that. So you will get the benefit of fast computations that and optimization that Neo4j provides. Okay. So, but I'm talking a lot, and I will show you. We will do same as before. Okay. We start the server. The difference with respect before is that we are running this generate network. So we will not start with 3 initial towers, but we will start with 8. Okay, and if we query, you can see that now we have 8 towers. Every time we restart the server, we will get a new random arrangement of nodes, okay? Because, well, it's random. Let's say, given this arrangement, okay, this is the network that we have now in our application, okay? So it's interesting to check, okay, which of these, I mean, this is relatively simple, but which of these will have the highest criticality score or relevant score, okay? So what we can do is go to our GraphQL endpoint, and we want just to compute the relevance, okay? This is because I need to refresh. And if I run this, okay, what we will have is we will get a list of relevance, and we will get the tower ID 1 with the highest score, then 0, then 6, then 2. We can put this one in front of the other and check whether that will be the case. I mean, according to the computation, this node is more critical than 0, that you may think that it's not. And then will be number 6, which is this, and then number 2, which is this one, okay? So we find a valid, or we have developed a valid tool to measure the complexity. Well, first to have a network, and then to measure the complexity of the network or the graph, okay? So the other mutations that we defined before still work or should work. So imagine that, okay, this is my current network, but I'm not happy and I want to remove the tower with ID 2, okay? So I run this, and then if, yeah, get in mind that 2 is here in the middle. If I query again the same network, you see that number 2 is not here anymore, okay? Basically, we change the topology of the network. So this is important because maybe, or to simulate what could happen with the network in case we remove data, okay? And the mutation of adding tower will work too. And you might think, and this is the last step. I mean, we have the whole application that provides a solution for the use case. And you can say, okay, but this is really, really simple, Javier. So what is the benefit? And the benefit is, imagine that we have much more complex network. Imagine that we have not 100, but 50, and we have just one more degree of connectivity, and we save it, okay? And we query again the network and look at what we have. Before, maybe by eye, you can say, okay, this tower is more critical, but in this network, I mean, I agree with you that it's random and it's not, it's purely toy example, but can you measure by eye something here? It's really difficult. The solution that we have, still we have this complex network, we can still compute how relevant or what is the most relevant tower, and we will get that the most relevant is number tower 2 with this score. And well, you can, if you are the owner of the telecommunication or communication company, you can adopt some measures. Okay, so this is the last step, and this is the end of the session for me today. I would like to make with you the summary. So my summary is that the Python ecosystem provides already some tools to work with GraphQL. I know that JavaScript is much more powerful in this sense. The JavaScript ecosystem is more mature. There is a whole stack called the Grand Stack, based on React and Apollo for this. But I think we in the Python community, we also have some tools to provide value. The second point that I would like to remark is the potential of solutions like Neo4J that performs complex operations really fast because they are optimized for that. And not only that, it will give an extra layer of abstraction, which is the giving a proper entity to the relationships between other nodes, okay? And this is really important. Comparing the classical REST and the GraphQL, I see the point and why many people are migrating to GraphQL. The good thing, for instance, in Fast API is that you can have both, okay? You can have your REST API implemented in the classical way. In parallel, because will not collide, you can start developing the schema that will give access to the GraphQL solution or schema. In addition, GraphQL allows you to provide an abstraction layer on top of different data sources. The resolvers and the mutations that we have done is written by us. So what if I want to use the result of this score and another third-party API or another third-party database? I can mix both informations and present it to the user as a single result of a query. And I think this is really powerful and flexible because you don't need to have fixed schemas. You just have to, or fixed endpoints, sorry. You just need to have an schema, which is a contract, and then start giving access or resolving the part of the schema that you want to give access. I think this is enough for today. I hope you enjoyed the session. I recommend you to go to the repository to read the code of the 5 branches, especially branch number 5, the step 5, and play around and understand the logic in Graphene and in Neo model and Neo4J driver. Okay. And now, well, I would like if to open the microphones to any of you that has any question or to have any final idea or summary about the experience of this. If not, also let me know and we will finish here.
So thanks, Javier. That was a very interesting talk. And you can reach us on social media, Twitter. We're there as well. So feel free to contact us. Yeah, thank you all for attending.
Thanks for coming, and remember that you have all the information in the repository. Cheers. And have
Thank
a
you,
good time.
Javier.
Thank you. Cheers.
Bye.
See you soon. Ciao, ciao.